Does anybody have any questions from what we looked at yesterday? Talked about distance formula. We talked about equation of a sphere, talked about a midpoint formula. Basically, those things were just extensions of concepts that we should be familiar with already. Okay. And we went through examples, and I think it wasn't too stressful of a material to go over. Okay. All right. Hearing no questions, we're going to get started into talking mostly about vectors. Okay. First thing I want to talk about, though, is the equation for a plane in Cartesian space. Okay. Just like a line is kind of the most basic unit on two-dimensional object. Okay. The most basic three-dimensional would be a plane. And you can think of a piece of paper as a plane. Okay. This is the XY plane right here. It would really extend in both directions infinitely. I mean, all four directions infinitely. Okay. But planes in Cartesian space, this kind of extends off of what you would have learned about lines. Okay. This is a general equation for a line. Okay. But if we just extend that to having another coordinate there with z, okay, it's not just ax plus by plus c equals 0, but ax plus by plus cz plus d equals 0. It says where a, b, and c are all not 0. They all can't be 0. If they're all 0, then you have nothing. Okay. All right. But that, just as this would form a line, which is a basic unit of the rectangular coordinate system, what's circled there would form a plane. Right? We're going to look at an example of a plane here. And we're not going to spend a lot of time on it because it's not something we're going to dive into a lot here. Let's see. All right. I thought I had a diagram of a plane here. I guess I do not. Okay. All right. So if I'm going to go back a little bit here. Give me a second. Okay. But if we wanted to form a plane, okay, for example, this side of this box right here, I'm going to outline it. That would form a plane. Okay. It would be, looks like it would be parallel to the y-axis. Okay, that would form a plane right there. All 6 of those sides of that cube would individually form a plane, and there's all kinds of planes. We could form a plane that goes, this way. Okay, that's supposed to look kind of diagonal there. Right. We would have to come up with the equation of that one, but we're not going to do that at this time right now, but we could definitely do that. All right, so I just wanted to kind of look at a plane, a picture, an idea of what a plane looks like. So just think of each of those 6 faces of that cube would be a plane itself, if we extended it in all directions. Let's get ahead here. And let me go back here again. Each of those, each of these planes, there's basically 3 planes there that divided our 3 space into the 8 octaves, right? Each of those would be a plane in itself. Remember that it would extend all the way up and all the way down. If you watch, some of you guys watch football, right? They talk about in football, you have to break the plane. Mm-hmm. Okay. Basically, that's a line at the goal line that goes all the way. It goes up infinitely, right? It stops at those 2 pylons at the end of it. It's just a plane. It's a barrier. Okay. So let me scoot ahead here. So I just wanted to get an idea of what a plane looks like. Not an airplane, but a plane in 3 space. Now, vectors. All right. Once again, we would have talked about vectors if we went through chapter 6. We didn't have to in the when we were discussing our dual credit in the first semester. So that's basically the one chapter we did not go over. Okay. But in 3 space, okay, a vector is basically something that gives you both a direction and a magnitude. Okay. A direction and a magnitude. Okay. Think about it this way. If you were navigating an airplane, you might go on a specific vector. You know how fast you're going and you know the direction you're going. Does that make sense? Okay. Anybody's ever seen the movie Airplane? It's really old. What's your vector, Victor? Remember that line?
Sure.
Do you do or not?
I watched it a long time ago.
Okay, but anyway, it's a spoof movie.
It's really weird.
It's funny, right?
Yeah.
It's stupid, but okay, it was from the 70s. That was like a comedy back then. Okay. Kareem Abdul-Jabbar, yeah, he was in there. But in the movie, that they're in the airplane and they're talking about what's your vector, Victor? Because the guy's name is Victor. It's just kind of silly. The other good line there is, surely you must be kidding. And I never kid. Don't call me Shirley. Yeah, that's that kind of stupid humor from back then. So, good stuff here. All right, so a vector gives you both a direction and a magnitude. Now, technically, if we're talking about a vector with respect to an airplane, we could have it in free space because we could be going at an elevation. But in an airplane, we're thinking once we get to a certain altitude, we're not going to worry about that third variable, right? Because if we stay at that altitude, we're on that plane. Okay. Now, these values down here, this value of I and J, all right, I'm going to circle them, and K are called unit vectors. Okay, I think they're called standard unit vectors. Okay, basically a standard unit vector is going to be, it's going to have a magnitude of 1, and basically the standard unit vector in terms of x is 1, 0, 0. Okay, so it's going to go at something moving along the x-axis. Okay, the standard unit vector for going in a y direction is 0, 1, 0. Okay, so that's a vector with a magnitude of 1 moving along the y-axis. And the standard vector for z, which is, they call it k, is 0, 0, 1. That's basically something moving up the z-axis. Okay, they're called a unit vector because their magnitude is 1. Okay, it's like their length. Okay, and a magnitude of a vector is basically how long it is. Okay, how long it is. Okay. Now, most of the vectors we look at are not going to be unit vectors. They are going to be, a vector in this form. Okay, so it's going to basically give you a x coordinate, a y coordinate, left and right, and up or down, I suppose, if we're going downward. Okay, so most of the vectors we see are going to look like this. Now, the way you can tell it's a vector as compared to a point is vectors are going to have that type of bracketing around it. Okay, if it was to look like this, that's a point. This is a vector. Okay, see the difference? You can almost see it. It's almost like it has arrows, but we can use those less than or greater than symbols. Okay. Now, vectors aren't too terribly difficult to work with, but the next thing we're looking at is there's a bunch of properties of vectors, and they're located on page 633. All right. Vector relationships and in space, and it says for vectors v1, v sub 1, v sub 2, v sub 3, and w sub 1, w sub 2, w sub 3. Okay. Now, this maybe looks complicated, but it's not. Okay. And you're going to say, yeah, you say that because you've taught math forever. Okay. But these ideas aren't too terribly difficult. Okay. Basically, the first one here, it says equality. Two vectors are equal if their components are equal. It's kind of common sense, right? X is like the vertical, the horizontal component, y is the vertical component, and z is the other component. Okay, in order for two vectors to be equal, their components must be the same. All right, not a big deal. Vector addition. Okay, we can add two vectors, and basically to add two vectors, you add similar components. Okay, you add x components to one another, you add the y components to one another, and you add the z components to one another. So you end up with a vector or like this. Okay. Subtraction works the same way. All right. You subtract the components that are alike. It's basically like adding or subtracting like terms. Okay. All right. Now, earlier I said we talked about the magnitude of a vector. And we said magnitude was I said that was the length of the vector. Okay. Was the length of the vector. What does this little formula right here? First of all, magnitude is kind of the absolute value of something. That's what we call the magnitude. What does that little formula there look like? The square root of v sub 1 squared plus v sub 2 squared plus v sub 3 squared. What does that maybe look like? Something we did yesterday. What does it kind of look like? It kind of looks like the distance formula. That's exactly what it is. Okay. We're basically, if we're talking about a vector, we're basically saying that vector has an initial point generally of 0, 0, 0. Okay, so if we are going to find its magnitude, we're going to find its distance from 0. That's how long it is. Okay. All right, so once again, when we give reference to vectors, we're giving them from that origin. Okay. Now, dot product, I don't know that we're going to deal with that a lot, but there's how we can find it. Basically, it's going to be the product of components that go together. All right. And if we ever want to find a unit vector, that's basically changing a vector to a magnitude of 1. Right. That would look like this. All right. We're going to use some of those things in a few minutes here, but I don't think we'll use a lot of the dot product, I'll be honest with you, or the unit vector, but just be familiar with them. And you don't have to memorize this stuff. If you have it written down, you can use it if you need to. Okay. And once again, this is on page 633. All right, so we might do a little computation with vectors. Okay. Questions on that? All right, so I'm going to grab my little notes here. So let's look at an example here, and I'm just going to go to the whiteboard here. All right, so I'm gonna make a couple vectors up, and we're going to work with them just to kind of show you it's fairly easy to work with. All right, so let's say we have vector v, and I'm just going to make it up. 1, -2, and let's go 4. Once again, I'm just making this up. And I'll say vector w is -2, 0, and 3. Okay. Just made those up. They're not significant for any purpose at all. So if I wanted to find, I'm just going to go back to the textbook on page 433 just to look at those. Obviously, vector v is not equal to vector w, right? They're not equal because their components aren't the same. Okay, they are not equal. Now, the vector v plus w would form a vector in itself, and it would be -1, -2, and 7. Any problem with that? All right, that's vector addition. Added the components that kind of go together. X, Y, and Z. V minus W would also be a vector in itself. That's going to be 3, -2, and 1. Once again, instead of adding, we're subtracting. So like I said, I'm trying to show you that working with vectors isn't going to be too terribly difficult here. Okay. Well, now let's find the magnitude of vector v. We could find the magnitude of w also, but I'm just going to choose vector v here. So that should be the square root of 1 squared plus -2 squared plus 4 squared, which is going to be the square root of 21. 1 plus 4 plus 16. I did that right. So basically, that's how long the vector is. That's how far from the origin it is. Square root of 21 units. And we can't break down the square root of 21. Okay. Now, once again, I said we're not going to do this a lot, but I'm going to find the dot product of these two vectors, just because I'm going to show you how. It's not, like I said, it's not complicated, but we'll go through it. Basically, the dot product basically says we're going to take 1 times -2, and we're going to add -2 times 0, and we're going to add 4 times 3. That would be our dot product of that vector. There are applications, I don't think we're ever going to get to them, but there are applications on the road where you may find the dot product of a vector. And I think my math says that's about 10. -2 plus 0 plus 12. All right, I just want to walk you through it. Hopefully you're seeing that's not complicated to do. All right, we're not going to worry about the application of that. Now, the last of those vector relationships in space was the unit vector. Okay, unit vector would be the vector. I'm going to find the unit vector of v divided by its magnitude. Okay, which would look like this if I simplified it. Really, this is how it would work. And maybe I'm not going to like the way it ends up here, but I'll have to deal with it. Is that really kind of just distributing that magnitude through there? Yes. So it's not, like I said, I don't like leaving the radical on the bottom. We could clean that up, but that's not the main focus here. Okay, that's not the main focus here. Okay. So vectors aren't too difficult to work with when we're doing vector math, I would say. Okay. All right. Questions? All right. And is anybody here taking physics right now? If you do, you are anyway. If you end up taking physics, you'll deal with vectors. You'll probably go more in depth with Mr. Nielsen. Okay. You gonna take physics next year? Why not? Because you're gonna just slide next year? Mm-hmm. That's what I would do too. Good plan. You can take calculus, all right? Why not?
It didn't fit in.
That's fine. I don't care.
With my arts and my
Did you really want to take it anyway? Be honest, you don't want to. That's fine. Anybody taking calc next year? Good. Got some people that are afraid. I'm kidding.
I'll still see you in the hall.
I know. You're gonna miss me. That's what it is. No, I'm just hoping there's enough people for the class. Sometimes we don't have enough. It's worthwhile, I think. But obviously I would. And I'm just giving you grief. Besides, if you're not going into something that you would ever need it, any math related field, it's kind of like, what's the point, right?
Are we done for that?
No. What did I'm looking for my PowerPoint here. God dang it, where'd that go? What did I do wrong now? It's because I did this, that's why. All right. So, we scoot ahead here. This is what happened yesterday. Now, last thing we're not done. Last thing we're gonna talk about, I'm gonna see if this shows up here. Remember yesterday how I had that trouble with things? If that disappears, I think I figured out the trouble. All right. Now, equations for lines in space, okay? Equation for a line in space. All right, that's the next thing we're gonna look at. There's two different forms, and that will be it after that, Anno. We'll be done then. Okay, all right. Now, when we're talking about equations for lines in space, there maybe is a little bit more to it, a few more moving parts. Okay. Basically, when we're talking about lines in space, we need to have a point that the line goes through. Okay. And we need a direction. Is that a lot like saying we need a point and a slope? Is it slope kind of direction? When we're talking about on our XY plane? Yeah, it should. It is, okay? Okay, it is. So we have two forms. We have a point that the vector goes through, and it's going to go in the direction of that vector. Okay, that's what we're dealing with. So it's, like I said, I equate that to point and slope. Now, the vector form, and once again, these are on the bottom of page 634 if I move away from this here. The vector form is R equals R sub 0 plus TV. Okay, and we'll talk about how that I mean, I'm just running it bigger here. All right. That's called the vector form. Now, what would that look like? Well, we'll get to that in a minute. Okay. So that looks strange now, but we'll look at an example where we use it with a point and a vector in a second, okay? I'm just making it larger. Now, vector form, remember, or parametric form, excuse me, when we talked about parametrics, we said both x and y depend on time. We did that a long time ago. So instead of having y in terms of x, we have x in terms of t and y in terms of t. Well, now since it's in 3 space, we're gonna have z in terms of t also. So I'm gonna say this is vector form, parametric form, and I don't know why I'm writing it down, but I am, because it's right there, but is x equals x sub 0 plus AT, y equals y sub 0 plus BT, and z equals z sub 0 plus CT. Okay, that's the parametric form. Okay. Now, if we get it in vector form, parametric form kind of falls into place. Okay. Now we're basically saying vector form, we're basically saying R is a new vector. Okay, R is like a new vector, or it's a line, I should say. Okay. Now, like I said, this might look complicated because all these variables are in there and such. It's not. Once we look at an application, well, I think you'll see that things will fall into place, right? Trust me. Okay. So once again, this equates to knowing a point and a slope, just like we did for a line in the coordinate plane. All right. So let's look at an example here. I don't want to do that one. All right. So I have a problem that I have ready here. So I'm going to go to the whiteboard here. Okay. So we want to come up with an equation for a line in space. And we're going to look for it in both vector form and parametric form. And I'm going to say the initial point is 2, -1, 5. And in the direction of 3, 2, -7. Okay. I want to come up with both the vector form and the parametric form. Okay. So let's go to the vector form first. Okay. Well, that says R equals R sub 0 plus, I think it's VT. Was that right? Or TV, VT, whatever. Right. Well, this is our initial point, which is right there. And this is our vector, which is right there. So this is just a matter of saying R is, make sure I write the correct way. That's a negative there. And I wrote it a little bit different way. Okay, that would be the equation of that line through that point in that direction. Does that look like slope-intercept form?
Would the points have parentheses instead of?
Let me double check. I know let me make sure. I know what you're asking. Yes, it will. Okay. She's asking, because this is called vector form, so we're going to write it as a vector. Does that make sense?
Okay.
But this is what you're asking about. Should those have those brackets around it? Yeah, they should. Okay. So really, that's, I mean, when you think about it, that equates to, this kind of looks like slope-intercept form to me. I'm right. I'm changing the way it looks. Kind of looks like that, doesn't it? Okay. In the direction of this vector, that's like our slope. This is our point. Maybe it's more like point slope form, but to me, it more looks like slope-intercept form. Okay. Now, if we're going to go to parametric form, once again, we're going to realistically, we're going to, we can work off of this one right here. Okay, we can work off of this one right here. Our x component is going to be 2 plus 3t. 2 plus 3t. That's our x component. Y is going to be -1 plus 2t. It's like our initial point plus our direction. Now I'm going to let somebody else figure out what would our z component be. I'm going to go -7t, but that's correct. Yep. We could go plus a negative if you want to. All right. So it looks complicated with r and r sub 0 and v and t and all that other stuff. But we just have to equate it back to something we are familiar with. It's kind of like a point slope form of a line or a slope intercept form of a line. What's different is we have 3 components rather than 2. Okay. All right. Questions? All right, here are some things to work on for tomorrow. Tomorrow we're going to go over any questions you have, and we'll start looking at review questions for the quiz, which we'll go over on Monday. So we have a quiz next Tuesday, and then we'll move on into chapter 9 later next week. Okay. So that's what we should be. A little bit of time to work on some of those things. This is more of just a familiarity with vectors. We're not going to become experts at them. We're going to go that route.